Welcome to part 2 of taking the mystery out of pi. Now, when we left Mac at the end of part 1, he was feeling pretty fat and happy. He had 3 lumps of cheese in his belly. He was feeling pretty smart. He was answering all these problems and had pretty much figured that he had gotten this whole cheese thing figured out. But then one morning, he wakes up and this is what he finds. Oh my word, what on earth is this? There's a pie dish there, sitting there right in front of his mouse hole. The pun is intended. Now Mac, he would just die to run straight across the circle. He would die to run across the diameter of the circle and just get that cheese and get back really quickly. But he can't. This is something in math that we call a constraint. Mac is constrained. He is unable to run straight across that circle and get the cheese. No! Mac has to run around the circle. The poor little guy, look at him. He's got to run all the way down here, even though the cheese is just to the right of him. And then he's got to run back up to get the cheese. And then he's got to run all the way up here to the top of the circle, and all the way back down again, just to get back to safety. Oh, what a mess! So Mac is getting desperate. He hasn't eaten for days. Look how small he's gotten. He's shrunken back to his original weight. This is awful. So Mac wants to have some kind of idea about what the circumference is. What's circumference? Well, circumference is just the distance around the whole circle. The word circumference even sounds like circle, doesn't it? So what Mac wants to know is he wants to know what the circumference is of this circle. And he's desperate. He doesn't need to know it exactly. He just wants to have some rough idea of what he's in for if he starts running around this pie tin and Kruger starts chasing him. So he just wants a rough idea, an estimate of what the circumference is. So I want you to think about this. We have a circle. It has a diameter of 1 foot. That's the distance across the circle. And I just want you to come up with a rough idea of what you think the distance would be for Mac to have to run all the way around the circle, the circumference. So it's time to pause and ponder. Okay, before I give you my answer for this, I want you to think about one thing. Can you come up with some lower boundary, lower bound on what the circumference must be? In other words, can you come up with a number that's so low that the circumference is guaranteed to not be less than that number? The circumference must be bigger than this lower boundary. Can you come up with a number like that? Pause and ponder on that for a moment. Okay, this was a hard question, and it's possible you might not even have understood what I meant by lower boundary. So let me just get into it here with you. Now remember I said that Mac would die to run across the diameter, right? Just thinking about it, it's much shorter distance for Mac just to go in a straight line and get the cheese. So if he just went in the straight line to get the cheese, that would be 1 foot. But no, Mac can't do that. He has to run all the way around this circle. And clearly, going all the way around this circle is a longer distance than just going straight to the cheese, right? I mean, if you had a choice, you would just run in a straight line, right? You wouldn't want to go all the way around here if you didn't like running a lot, right? So clearly, this distance going from here all around the circle and then back up to the cheese has to be more than 1 foot, just the straight line distance. And this distance up here also going around the circle also has to be bigger than the 1 foot that Mac would travel if he could just go straight across the diameter like he would like to. So we have a number that's bigger than 1 foot, the lower part of the circle, and another number that's bigger than 1 foot, the upper part of the circle. And when we add a number that's bigger than 1 to a number that's bigger than 1, we get a number that's bigger than 2. Yeah, think about that a little bit if you need to. Right? But bigger than 1 plus bigger than 1 means bigger than 2. So that means that the circumference, the distance around the whole circle, the lower circle and the upper circle, is bigger than 2 feet. Now I want you to try to find the upper boundary on this. can you come up with a distance that is so big that we can pretty much guarantee that that distance is larger than the circumference around the circle? So see what you can come up with for this one. This one's a little harder. There's no one right answer for this. Just see if you can come up with something, even if you're just estimating it and saying, well, it looks to me like the circle would have to be less than something. You know, that's also fine. Just give it a little thought. Time to pause and ponder. Okay, I want to emphasize here that there are many possible right answers to my last question. And what I'm going to do is I'm going to share with you a way that I use to figure out a possible upper bound for the circumference of the circle. So what I'm going to do is I'm going to redraw the circle. I'm going to make it look larger, but it's still the same circle as before. The diameter that Mac would just die to run across, the diameter is still 1 foot. And the trick that I'm going to use is that I'm going to circumscribe a square about the circle. Circumscribe, it's a big word. What I'm basically doing is I'm drawing a square, the smallest possible square, that is completely outside of the circle. It just grazes the edge of the circle on the 4 sides. But other than that, it's completely outside of the circle. Okay, so what I want you to do is I want you to estimate, not to estimate, I want you to actually determine what the distance is around this red square. I want you to figure out what the perimeter is. That's the distance around the red square. Perimeter is the distance around a square, and circumference is the distance around a circle. So it's time to pause and ponder. Okay. Just in case you weren't able to figure it out, let me give you one more hint. The distance across the circle here, the diameter, is exactly the same as this distance down here, this lower distance, this lower length across the square. Does that help you? Are you able to tell me what the perimeter of the red square box is now? Pause and ponder. Okay, hopefully you noticed that each side of the square has to have the same length as the bottom side of the square. So that would mean that our total distance would be 1 plus 1 plus 1 plus 1, 1 foot for each side of the square. Or you could say it's 1 times 4, 1 foot 4 times, or 4 feet. Now the next question is, what does this clue, what does this 4 foot distance, what kind of clue does that tell us about what the circumference is, what the distance is around the pie dish? So I want you to pause and ponder on that for a moment. Okay, well let's look at 1/4 of this at a time. Let's consider running along the circle from here down to the lower part. And let's compare that with running along the square from here down to the lower part. Now, if you were lazy or if you wanted to avoid Kruger, which one would you rather do? Would you rather hug the circle and stay really close to the circle, or would you rather go all the way out here and then all the way back over here? Which one would you rather do? I'm hoping that you see that this distance along the red square is a longer distance. You're going way out here just to get all the way back here. It's not nearly as direct and smooth as just going along this circular line. So what I'm trying to show you is that this distance along the square is bigger than this distance here along the circle. Okay? And the same thing is true here. This distance here along the square is bigger than this distance here along the circle. Ditto for up here, for this part. And then the same thing for this last quarter of the circle and the last quarter of the square. So if each quarter of the square is bigger than each quarter of the circle, then that means that the whole square is bigger than the whole circle. Think about that a little bit if you need to. But if each quarter of the square is bigger than each quarter of the circle, the whole square is bigger than the whole circle. So what that tells us is that the whole square, which we already figured out is 4 feet, is bigger, it has to be bigger, than the circumference, than the distance around the circle. So that's what that's telling us, is that the circumference is less than the 4-foot distance of going around the square, because we know going around the square is bigger than going around the circle. Okay, I think I said that enough, hopefully. Okay, and we also know from before that the circumference is bigger than 2 feet, right? It's bigger than just going straight across, back and forth across the diameter. Now, there's a really neat way of writing this very, very concisely, and a really neat way of writing this in math. Let me show you how we do that. First of all, we start by saying that the circumference is bigger than 2 feet, okay? But then, without even going to a separate line, on the same exact line, we can add that the circumference is less than 4 feet, right? So it looks really nice, right? The circumference is in between 2 feet and 4 feet. Spend a minute and study that if you need to kind of convince yourself how this works. But we have that the circumference is bigger than 2 and less than 4 feet. So what do we want to give as our estimate now for the circumference? Mac's still looking for an estimate. So what we're going to do here is we're going to split the difference, and we're going to say the circumference is roughly equal to 3 feet. Now you may be wondering what these squiggly lines are. You know, what are these? Okay, this is the way I like to think about it. Mathematicians are usually pretty sure of themselves, right? I mean, they should be. They're thinking about math all the time, and they're usually right. And usually, when they write their equal signs, they write them with nice, solid, straight lines. But sometimes mathematicians don't know exactly what something's equal to. And the way I kind of picture it is that when they do that, they're a little bit nervous about what they're saying, and instead of writing nice, straight, solid equal lines, they're handshaking a little bit, and you get these little squiggly signs. So these little squiggly signs mean that the way I think of it, the mathematician's a little nervous, she's nervous about it, and they mean approximately equal to, roughly equal to, maybe equal to, but, you know, probably not. We're not totally sure. Okay, so that's what those squiggly lines mean. So what we're saying here is we're saying the circumference is roughly equal to the diameter, which is the 1 foot, times 3, or to 3 feet, right? Because we're kind of splitting the difference here between the 2 feet and 4 feet. So Mac is now ready for his next challenge, and you guessed it. He now has a circle that has a diameter of 2 feet, and he desperately wants to know how far he's got to go. What is his new circumference going to be equal to? And again, he's desperate. He's still pretty hungry. He's just got that little lump of cheese in his belly, and he's just looking for an approximate answer. Squiggly lines. He's looking for an approximate answer here. So based on what we did for the first case here, where we came up with the circumference, and based on what we did when Mac was just running back and forth in straight lines, think about that too. Can you come up with a good estimate for what Mac's new circumference is? This is a very serious pause and ponder. I really want you to hit the pause button and think about this. This is where the real learning happens. So pause and ponder. Okay, the thing that I notice here is that the diameter is doubling from 1 foot to 1 times 2, or to 2 feet. Do you remember what happens when one of the distances double? That's right. All of the related distances also double. So in this case, our circumference is going to double from being about 3 feet to being about, you guessed it, 6 feet. If you were able to get this on your own, congratulations. This was a tough problem, and to get it, you had to put a number of concepts together. Alright, now the other observation that I would like to make here, it's a little less obvious than when Mac's going in straight lines, is that whenever we add 1 foot to the diameter, right, we're going from 1 foot here to 2 feet over here, then whenever we do that, we're going to add about 3 feet to the circumference. So we go from about 3 feet for the circumference to about 3 plus 3, or 6 feet for the circumference. So overall, our lengths are doubling from the first case, and when we add 1 foot to the diameter, we're adding about 3 feet to the circumference. And this is true because, maybe you guessed it, The diameter and the circumference are proportional to each other, and they go up together in a special way. In this case, the circumference is going up about 3 times faster than the diameter, so the proportionality constant is equal to about 3, and our formula now is, it's an approximation formula. Our formula is that the circumference is roughly equal to the diameter times this proportionality constant of 3. Okay, remember that rule that I was saying where you double one part of a shape and the overall perimeter of the shape also doubles? That rule doesn't just apply for straight lines and for circles. No, it applies for all kinds of shapes. If we double one part of a shape, and this isn't very important, we have to maintain the same basic shape, then the overall perimeter also doubles. It may be a little confusing. Let me give you an example of this. Here we have a picture of Kruger on a good day, and his perimeter is equal to 5 inches. So that means that if I trace along the outside of his face here, his happy face, that I'm saying that this is a 5-inch distance going all the way around Kruger like this. Okay? Now what I'm going to do is I'm going to make a clone of Kruger. It's hard to say, a clone of Kruger. So I'm going to make a copy of him down here. And what I'm going to do is I'm going to double him. I'm going to stretch him from left to right, make him twice as wide as he was before. Here he goes. Look at him. He's getting fatter. And the question I have for you is, what is going to be the perimeter of the double-wide Kruger? Right? We know the perimeter of this guy is 5 inches. And we know that we're doubling all of our left to right distances. So the top of his head is just a left to right distance. So that has doubled. Whatever it is up here, it's twice as big down here. Okay? So the question I have for you is, I want you to think about what the perimeter is of the double-wide Kruger. So it's time to pause and ponder. Okay, so do you think the perimeter of the double-wide Kruger is 10 inches? Do you think it is doubled from the 5 inches because we made Kruger twice as wide? Are you sure of that? Is this your final answer? Are you really, really sure? No, it hasn't doubled. It doesn't double. I'm hoping you didn't say that. I don't really know what you said, but I'm hoping you didn't say that it doubled. But if you did, I understand. It's a bit of a trick here. The reason it doesn't double is that this Kruger has a different shape than this Kruger, right? We could call this one a skinny Kruger and this one a fat Kruger. There's a different shape. Even if we walked away from the computer and looked at the fat one from a distance, it would still look fat. It would just look smaller, right? Because this Kruger is much wider than he is tall compared with this guy. Right? Now, both of these Krugers have the same height from top to bottom. Right? So those distances, like the more up-down distances, don't change very much. The distances that go from left to right change by quite a bit more. So think about it a little bit more. Can you give me a range? And I'll tell you right now, we cannot get an exact number for this perimeter for the fat Kruger. But what we can do is we can come up with a range. Can you give me a lower bound that this perimeter must be bigger than? And can you give me an upper bound that this new fat Kruger's perimeter must be less than? Pause and ponder on that for a moment. Okay, this is a hard one. And even after I explain it, don't worry too much if you don't completely understand what I'm saying here. I'm hoping you do, but it's a pretty tricky idea. Alright? So when I compare the little Kruger to the fat Kruger, the thing that I notice is that all the parts of the fat Kruger are at least as big, if not bigger, than all of the parts of the skinny Kruger. Right? So like this top part here is twice as big. Right? When you compare it to the skinny Kruger. This part here, which is pretty vertical, is maybe just a little bit bigger, but not too much bigger. So since all of the parts of this Kruger are at least as big, usually bigger, than the parts of this Kruger up here, we can say that the perimeter of the double-wide Kruger has to at least be bigger than 5 inches. It's got to be bigger than this guy because all the parts of this guy are bigger than or maybe equal to all the parts of this guy. Now on the other hand, the biggest one of these parts can be on the fat Kruger compared to the skinny Kruger is twice as big. They can't be more than twice as big, right? So this top of his head is twice as big, but then when you look at this thing, which is pretty much up down, you know, from top to, you know, just kind of going straight down almost, that's not twice as big, that's less than twice as big. So the perimeter also has to be less than, going the wrong direction, has to be less than twice the perimeter of the skinny Kruger. So we know that the perimeter of this double wide Kruger is somewhere between this guy's perimeter and double this guy's perimeter. So it's somewhere between 5 inches and 10 inches. So that still begs the question, well, what do we have to do to double Kruger's perimeter? What else do we have to do to make this shape the same basic shape, just bigger than this shape? So pause and ponder on that for a moment. Okay, remember the basic problem that we had before is that we stretched Kruger from left to right, and that gave him a different shape. It made him look fatter, and it didn't quite double the perimeter, right? Because not all of the distances doubled, right? Some of the distances stayed almost the same. So in order to double his perimeter and also to keep the same basic shape, what we need to do is we need to double the vertical. We need to double the height of Kruger also. If we double his width and we double his height, let's see what happens. So we're going to double his height now. There he goes. He's getting bigger and bigger and bigger. And now he's twice as high as before, and he's twice as wide as before. So the question I have for you is this bigger Kruger the same basic shape as the original Kruger? He's obviously bigger, but is it the same basic shape? If we were to back up from the computer far enough so that this shape looks small, would it kind of look like the same shape as this one does when you're looking at it up close? So pause and ponder on that for a moment. Yes! This new Kruger has the same basic shape as the previous Kruger because we doubled both the up and down and the left and right. So it's the same basic shape. So the next question is, what is the perimeter of this double wide and double tall Kruger, right? He's twice as wide and he's twice as tall as the previous Kruger. Is it 10 inches? Pause and ponder for a moment. Yes! The perimeter of the new Kruger is twice as big. It's 10 inches, which is double the 5 inches, because all the parts of this bigger Kruger are exactly twice as long as all the parts of the little Kruger. Like this line here, it's going over, it's going left and right twice as much, and it's going up and down twice as much. So this little line is doubling, just like all the other parts of Kruger are also doubling. And if all the parts double, then the whole perimeter doubles as well. Okay, hopefully you can see now that if you double one part of the figure, but keep the same overall shape, that the overall perimeter of the shape also doubles. Likewise, if you were to triple or quadruple one part of the figure and still keep the same overall shape, the overall perimeter will also triple or quadruple. It's a general concept. So now Mac is finding himself in an even dicier situation. He now has a circle with a diameter of 3 feet, and he just wants to know roughly, approximately, what is his circumference, what is his distance going to be around this circle. And I don't want you just to tell me that. I want you to try to compare this case with the first case, and I want you to compare this case with the second case. And again, don't blow through the pause and ponder here. I really want you to think about it. This is where the learning happens. This is where the mathematical magic happens. And again, Mac is just looking for a rough guess for his circumference. So this is a serious pause and ponder. Okay, hopefully you remembered that the circumference is always about 3 times larger than the diameter. So in this third case, the circumference is going to be roughly 3 times bigger than the diameter of 3, or roughly 3 times 3, or 9 feet. Now when I compare this with the first case, what I notice is that the diameter has tripled. It's tripled from 1 foot to 1 times 3, or 3 feet. Remember what happens when the diameter triples, or anything triples. All of the related distances also triple. So our circumference is also tripling from roughly 3 feet to roughly 3 times that amount, or 3 times 3, or 9 feet. Now when I compare this with the second case, the thing that I notice is that the one-way distance is increased by a foot, from 2 feet to 3 feet. And remember, every increase of 1 foot to the diameter means that Mac has to run about an extra 3 feet around the circle, an extra 3 feet of circumference. So our circumference is increasing from about 6 feet to about 6 plus 3, or about 9 feet. So overall, our length tripled. All of our lengths are tripled when we compare to the first case. And when we compare to the second case, we're adding 1 foot to the one-way distance, and that gives us an extra 3 feet added to the circumference. So congratulations, you've made it through the second part of this video series. And we're now ready to start talking about pi. To continue, select Taking the Mystery Out of Pi, Part 3 of 4, from the Math from the Gut video link.